Here we go. Let's get on with another lecture. And we're going to talk about some exponential functions this time. So we've seen lines, we've seen parabolas, we've seen a couple other types of functions as well. But here we're going to focus more on exponential functions. And in this focus, we're going to actually really hone in on an application of exponential functions, which is compound interest. And this will be kind of a look ahead at the financial math section of the course. So we'll kind of get into what compound interest is and kind of looking at money a little bit and why interest is important. So let's go ahead and get right into that. We've talked about what an exponential function actually looks like, and this general format here is that we have our a to the x, that's our exponential part. So we have our base, which is a constant a. That could be any number like 2, -2, 1, but that wouldn't be very interesting, but you could have it. You could have 17, you could have really anything. And then our exponent is our variable, and that's our x right there. You can also just multiply it by a constant out front. You could also add something out front here, but we're not going to bother there. So if I have c times a to the x, that's my general format of the exponential function there. And with that, we're going to take a look at a graph here. So this graph right here is me actually graphing 2 to the x. So I'll go ahead and label that. This is f of x equals 2 to the x. And what you'll notice here is that the y-intercept here, if I set x to be 0, so if I evaluate f of 0 equals 2 to the 0, that's going to be equal to 1. And so my y-intercept is going to be 0, 1. And we see that right here where we have our y-intercept right there. Now, what you'll notice here is that in this general format where I have f of x equals c times a to the x, right? Maybe I don't have just specifically 2 to the x. If I take f of 0, what you'll notice here is that a to the 0 term, it ends up just being 1, and so I get c. And so a great sort of shorthand for finding the y-intercept of an exponential function is just to look at this value of c right here. And we saw that before with parabolas. On a parabola, we had that that ax squared plus bx plus c, and it was just that value of c that was my y-intercept there. Here it's the same thing, it's just whatever this constant c is that's being multiplied out front. Be careful, if I were to add 2 to this or something like that, that would actually change the y-intercept. That would move this entire graph up by 2. So just if you have this format, then that c is your y-intercept. But as we've seen, you can always just plug in x equals 0 to get your y-intercept and solve, so that shouldn't be too difficult. Great, so there's a graph of the exponential right there. We've got our asymptote that we've talked about here, where this doesn't ever actually touch the x-axis as I go more and more negative, but it gets very, very, very close, and it blows up to infinity as I get larger and larger on x. Just a recap here on some algebra, just so we don't run it, just so we sort of touch on this so we don't have this issue again. If you have a negative exponent, so if our exponent here has a negative value, that does not give you a negative number. A lot of people, when they see something like 2 to the -5th, they will just do 2 to the 5th, which would be 32, and they'll just slap a negative sign on it, and this is bad. That's actually not what we do. What we want to remember, and this is just algebra, so this should just be recall, is that the 2 to the -5 right here, we can rewrite that as 1 over 2 to the 5th. We can take the reciprocal of it. And so it's basically when I have that negative exponent, I just treat it as a positive exponent, but in a denominator. And so then I end up with that 1 over 32. What this should tell you, or at least what it should allude to, is that if I have an exponential function, it's always going to be positive, unless maybe I slap a negative sign in front of it. But if I just have a function that's like a to the x, that's always going to be positive. And you can see that on this graph right here. The function doesn't exist down here in these bottom quadrants. The function is always positive here. If it looks like a to the x. If it's in a different format, then that's a different story. But if it's in that format of a to the x, then it's always positive. A little bit more algebra recall. If you have a fraction as your base, and then you raise it to some exponent, you can sort of distribute that exponent into each part. So if I had 1/2 raised to the 5th, that's the same as 1 raised to the 5th divided by 2 raised to the 5th. 1 raised to the 5th is 1, 2 raised to the 5th is 32, and so we get 1 over 32. What I do want to mention here, now that we've seen these two examples, so I first showed that 2 to the negative 5th was equal to 1 over 32, and then I showed that 1/2 to the 5th was equal to 1 over 32. You should be able to surmise from this, because these are the same, you should be able to surmise that, in fact, that 2 to the negative 5 is equal to 1/2 to the 5th right there. And so you could evaluate that way as well. Great. So there we go. We got some algebra recall there. Make sure you're good on that, because you will have to work with some of these exponents and bases being a little bit complicated. Let's get into a little bit more on exponential functions and their graphs. So we've looked at this general format: c, some constant, multiplied by a to the x, where a is also a constant. That's my base. Dependent on that value of a, we actually get a different looking graph here. In both cases, c is that y-intercept value, that y-coordinate of the y-intercept. But if a is greater than 1, we end up with this graph that sort of takes on this shape here, where as x increases, the graph increases as well. So this would be an increasing function. If a is between 0 and 1, then your graph actually decreases. As I increase in my x value, so as I increase in my x value there, then my function will actually decrease in its y value. And so the value of a is very important here. Like I've said, if a is in between 0 and 1, then I have a decreasing function. But if a is greater than 1, I have an increasing function. So that's about as much as we're going to talk about with the graphs and the actual function of an exponential. Let's actually get now into the compound interest here. So this equation that I've got boxed up here looks very complicated, but let me try and break it down a little bit for you. So what this says here, this is actually talking about if you were to do one of two things. If you were to take out a loan, or if you were to invest money maybe in a bank account or in the stock market or something like that. And in certain cases, this loan that you're taking out, or if you're investing in the stock market, it might be compound interest that is the scenario that you're dealing with. Let me be very clear too. If you're talking about a loan, if you're borrowing money from someone, interest is bad. Interest does not work in your favor. If you take out a loan for a car or for a mortgage on a house, interest works against you, because they're going to add interest to that loan, and you're going to have to pay them back more than what you originally borrowed. And so interest is bad in those scenarios. But if you're saving money for retirement, or if you're putting money into a bank, or if you're investing money in the stock market, interest actually works in your favor. And so a lot of times I'll use this word interest, and you have to be careful about the context in which I'm using it, whether or not it's a good or a bad thing. And that should be pretty clear. That's not something that I think should be worrisome for you guys, but just to keep a heads up there. So we've got compound interest here. Whether interest is good or bad, it happens. And let's take a look. A of t here, so this is my function a, and this is how much money I have after t years. So t is the number of years of saving or borrowing. Maybe I could throw that in here, saving or borrowing, depending on whether it's an investment or a loan. So t is the number of years that I save this money, and A is the amount of money that I have after those years. And so we actually have this nice formula for A of t, and it is given mostly by this exponential. And what we notice here is that t is my variable. This is like my x, if you will. T is my independent variable. It's my input. The amount of money that I have is dependent on the amount of time that passes. And you'll notice in this side of the equation, the only place that there's a t is in the exponent. And so that means that this is an exponential function, and it's dependent on t, right? And so this p, r, and n, the n appears twice there, those are all constants. Those are all set values that I'll either give you in a problem or I'll give you info such that you can figure out what they are. P is what we call the principal, and it's how much money you start with. So let's say that I invest, or that I go ahead and I put $1,000 in a bank account, even just a standard bank account, maybe with a bank like US Bank or Bank of America. You just put $1,000 there, and what they're going to do is they're going to tell you, thank you for putting your money in our checking account or savings account. We're going to give you 1% of interest per year, or maybe if you're lucky, they give you 2% of interest per year. So they give you a little bit of money, and that percentage that they tell you, that per year percentage, is an annual interest rate, and that's R, and that goes in right here. Be very careful. Annual is important here. For almost every interest rate that we see, it will be an annual interest rate. But for a select few, it is not annual. A great example of this is credit cards. Most credit card interest rates, they actually tell you the monthly interest rate. And that actually means that you'd want to take that monthly interest rate and multiply it by 12 to get the annual interest rate. They obviously do that because it makes the interest rate seem lower. If you say, hey, 2% per month, that sounds better to a lot of people than 24% in a year. So just be careful here. Most of the interest rates that we'll deal with are annual, but occasionally they will be monthly, or maybe even daily or weekly. But most of the time they're annual. So going back to our example here, you invest $1,000, or you put $1,000 into a savings account at a standard bank, US Bank, Bank of America, etc. And they tell you an interest rate, an annual interest rate, that they're going to give you some extra money as sort of a thank you for storing your money in their bank. And so they give you that annual interest rate R. And then N here is the number of times that they're going to give you that extra interest per year. So you can think about this. If you put $1,000 in the bank here, then they say, hey, we're going to give you 1% per year. Well, if they decide to give you that money once per year, meaning n is equal to 1, they give you they sort of add to your account. They add the interest into your account once per year. At the end of the year, they will add in 1% of however much money you put in, which in this case is $1,000. 1% of $1,000 is $10. So they're going to add in $10. But let's say that they tell you, hey, instead of adding it in once per year, we're going to add it in twice per year. Well, what they're going to do is they're going to say, hey, you put in $1,000 and we're going to give you 1% a year, but we're going to do it twice instead of just giving it to you once. So instead of giving it to you once at 1%, we're going to give it to you twice at 0.5%. And while that seems like it's the same thing, it's actually slightly different. We'll see several worksheet problems that explain that. But if they give you 0.5% after 6 months, and then they give you 0.5% again at the other 6 months, that actually works in your favor a little bit. And I know a lot of what I'm saying now might seem like a lot. Don't worry about it too much if it's not making sense. We'll see several problems down the line that explain what I'm talking about. But just to highlight these big things, T is the number of years that I save. A is the final amount of money that I have. P is how much I start with. So basically, I'm starting with P and I'm ending at A. R is the interest rate that the bank or the loan or whatever it is giving me, and N is the number of times that they add money into my account. Great. Talking more about this value of N, and this is just the wording of this. So we'll use certain words to describe the value of N. If I give you a problem and I say that the account is going to be compounded annually, that means that N is 1. If I say semi-annually, that means twice a year, so N is 2. If I say quarterly, that means 4 times per year, so N is 4. Monthly is 12 times per year. Weekly is 52 times per year. There's 52 weeks in a year. And daily is 365 times per year. I could even do something where I could say it's compounded every second, and you'll have to find out how many seconds are in a year. I could say it's compounded every hour, and you'll have to find out how many hours are in a year. And there's really an endless sort of combination there. So let's do an example here, and I'll kind of just go through this without much pause, just to kind of say, hey, here's how we do a problem like this. So let's say that I put $10,000 in the bank, and they tell me that they're going to give me 8% per year. So whatever is sort of a thank you for investing money in their bank, they're going to give me an extra 8% every year, and they're going to compound annually, which means that at the end of the year, they're going to give me that 8% extra. And after 40 years, I want to find how much money I actually have here. And so let me be clear here. Let's look at this for 1 year. So if I put $10,000 in the bank, and let's just say I leave it right there. I just say, hey, $10,000, boom, thank you. And you don't touch it. You don't do anything to it. Well, at the end of the year, they're going to give you 8% of your 10,000. Because you've put 10,000 in, they're going to add 8% of that into your account. And it turns out 8% of 10,000 is actually $800. And so what this means is that at the end of 1 year, you will have $10,800. But then guess what they're going to do? After another year, they're going to add 8%. But this time it's 8% of $10,800 because you have more money in that account now. Because you've left that money in the account, they're actually going to add 8% of 10,800. And while I can't do that math in my head right here, like I could do the 8% of 10,000 in my head. I can't do this quite in my head, but what I will tell you is that this value that I'm highlighting here is slightly more than the $800 that they added before. And so basically what's going on here is they're adding a little bit more and a little bit more and a little bit more each year. And so after 40 years, this might add up to be a lot. And let's actually go ahead and calculate that using the formula that we've seen right here. This formula will actually calculate that. Obviously, you could do this by hand 40 times. You could keep adding 8% and 8% and 8%. You could do that 40 times, but it's the same as doing this formula. And this formula is a lot easier to deal with. So let's go ahead and look at this. We start with 10,000, so P is $10,000. My interest rate is 8%, and so R is 8%, which is equal to 0.08. Make sure you always turn that percentage into a decimal and you don't just plug in 8 in for R. N is equal to 1 because we compound annually, which means 1 time per year, and T is equal to 40. So that's because that's the amount of time that I keep the investment for. So what you'll see here, I start off with this formula and I plug in 40 in for T. I plug in P is 10,000. R is 0.08 and N is just 1. So 0.08 divided by 1, I'm just kind of going shorthand here and I'm just saying, hey, 0.08. N times T, well, N is 1 and T is 40. So that's just my 40 right there. And what you'll notice here, I like to do this step by step and I like to be very careful with my algebra and the decimals that I use here. So I have 10,000 multiplied by 1 plus 0.08 to the 40. Well, first things first, we have to deal with the parentheses and what's inside there. So I add 1 and 0.08 and I get 1.08. At that point, I have to move on to the exponent. I don't want to take 10,000 and multiply it by 1.08. I want to take 1.08 and I want to raise it to the 40th. And when I do this, I get 21.724521. And what I'm doing here is I'm keeping a lot of decimals. And the reason for that is because I'm multiplying it by 10,000. And when I multiply by 10,000, it's going to move this decimal place over a good amount. And so I want to keep a lot of decimal places here at that point of the step. You'll do a lot of problems on these where you'll probably recognize fairly quickly that you want to keep a lot of decimals in these financial math problems, just because we're dealing with money and we want to have as many decimals as we can. I then take this and I multiply it by 10,000 and I end up with a whopping 217 grand. That's $217,000. And so what I like to do here, I like to show this problem at the very beginning of talking about financial math, because really what I want to make clear to you guys as students is that this is the basic idea of a retirement plan. If you can somehow scrounge up $10,000 right now, and I know, for a lot of you who might be, young and maybe you're just getting out of high school or maybe you're just starting off college, $10,000 is a lot of money. I get that. But if you can have $10,000 and you can put that away at 8% per year, which 8% per year is not that hard to obtain. It takes a little bit of work, but you can, with some work and with some knowledge, you can find an investment that's 8% per year. If you can find that, and if you have $10,000 that you can afford to save and put away, if you just don't touch that for 40 years, which is likely retirement, if you're, like I said, if you're a student who's just getting out of high school, maybe you're 18, 19, 20 years old. In 40 years, by the time you're 60, you're going to have $200,000. And all that you had to do was start off with 10,000, and you end up with over $200,000 in your account for doing absolutely nothing other than having $10,000 that you can put away. And so I like to show that here just to really emphasize the importance of saving and saving early. Really what makes this value, this 200,000 value, so high, it has nothing to do with this interest rate. It has nothing to do with the amount that you start with. It's really all about the time. Even if you invested $5,000 over 40 years, or even if you invested $10,000 at 4%, if you do it over 40 years, if you do those things over 40 years, over a long period of time, the amount of money really adds up here. We'll see some other examples here of how you can sort of deal with retirement funds, if you will, and how you can, invest your money to have a lot for retirement. And so we'll go ahead and call that as the lecture here. We've got this very first example of compound interest. We'll get into several more examples of this. Basically, we're just dealing with this formula right here for now. We'll get into some more complicated formulas in the next unit. But for now, we'll just deal with this formula and we'll go ahead and call it good. And so that'll be our lecture. There we go. See you next time.